In our previous tutorial, we introduced the electric potential. Now we are going to discuss about electric potential difference. Consider this tutorial a continuation of the previous one. It's Kisembo Academy, and thanks for tuning in. If this point has a lower potential and this has a higher potential, so the work done in moving this potential, this charge from a position of low potential to a position of high potential is what we are calling potential difference. In this tutorial, we shall derive the formula of work done in moving this charge from this point to that point. We all know that potential, the unit of the potential is called the volt, and which volt is equivalent to 1 joule per coulomb. So what is the volt? By definition, the volt is simply the potential difference between 2 points when the work done in transferring 1 coulomb of electric charge between the 2 points is 1 joule. And like earlier said, 1 volt is equivalent to 1 joule per coulomb. So let's go ahead and derive the electric potential formula. The potential difference formula. Here we are going to consider a charge Q, and we have also two other test charges. Now these charges A and B are lying on a line of force. The line of force is due to this charge Q. Supposing A and B lie on a line of force at a distance A and B separately from charge Q, we are having A lying at a distance A. We are also having B at a distance B. These are points along this line of force, lying on that line. Now when a unit charge is at a distance x from Q, this is the unit charge we are talking about. It is at a distance x from Q. While in free space, then the force acting on it. So now the force acting on this unit charge is we are going to get this force from Coulomb's law of electrostatics, which is going to be 1/4 pi epsilon naught times Q, the product of the two charges Q. The Q we are talking about is this charge Q, times this unit charge +1. So it is Q times 1 over x squared. So meaning that this unit charge can either move from B to A or from A to B. Now, if this unit charge is to move from B to A, it would mean that it's going to work against the repulsive forces of this Q, because this Q is also positively charged. So it means that work is going to be done against the forces of the repulsive forces of Q. And if this unit charge is to move from A to B, it means that this Q, this charge is going to do work in pushing it away. So now what I'm trying to say here is that the work that is done against the repulsive forces in bringing B to A is going to be the same as the work done by these repulsive forces in pushing A to B. So we continue with our write-up. Work done on taking the charge from B to A against F, or against the repulsive forces of the charge Q, is equal to the work done, or work which force F will do if the charge were allowed to go from A to B. The force F we are talking about is the force due to the charge Q, the force which we have gotten here as 1/4 pi epsilon naught times that. Now, over a short distance dx, the work done by the force F is given by the small change in work is equal to force times that small change in distance. That small change we are talking about is this. If this thing is to move, this test charge is to move from, let's say, that point to that point, and it is to go through a very small distance dx. So it means that the work done in moving from that, to move through that small distance, is going to be the force times that small change in distance. And that is what this expression means here. Now, what if we wanted to find the work done for that force to move the entire distance? By the entire distance, we are talking about if this test charge is to move from A to B, a significantly very big difference. So meaning that over the whole distance AB, work done by the force on the unit charge that is work done to move from A to B, is going to be equal to force times distance. So it means we are going to integrate from the point when x is equal to A to the point when x is equal to B. And these distances are the distances from the charge Q, capital Q. So integrating that would give us, we substitute for the value of F, and so it means that work is going to be equal to Q over 4 pi epsilon naught, which is the F we have substituted, multiply that by 1 over x squared. This is Coulomb's law, we've just substituted for F, dx. And it's running from A to B. Now if you realize Q over 4 pi epsilon naught, this is a constant, so we'll put it outside the integral sign, and inside will remain with 1 over x squared. So 1 over x squared is what we shall integrate. 1 over x squared is the same as x to the power negative 2. So x to the power negative 2, integrating x to the power negative 4 running from A to B is going to be equal to x to the power negative 2. We add 1 to the power, and the answer we get here we divide by the whole term, like illustrated here. And so negative 2 plus 1, here we get negative 1. Negative 2 plus 1, we shall get 1. Negative 1. And that's the negative that is going outside here. And so when we are to substitute in our expression here, we are going to end up with negative Q over 4 pi epsilon naught times 1 over x. X to the power negative 1 is the same as 1 over x. It's running from B to A. Substituting B in this expression is going to be 1 over B, minus substituting A in that expression is going to be minus 1 over A. That's the expression we have. So multiplying this negative through these brackets, it would mean negative this times 1 over B and negative this times that. It would mean that this is going to become positive 1 over A. So that's how this comes to this. We have this as positive, which is equal to 1 over A minus 1 over B. And that will be our expression for the work done. If you want to watch more of these videos, simply subscribe to this channel, and for the benefit of your colleagues out there who would like to watch this tutorial, simply share this video. So this is our expression for work done. Work is going to be Q over 4 pi epsilon naught into 1 over A minus 1 over B. But we are interested in finding the potential, not the work done. So how do we get the potential? Remember, in our definition of potential, when we were introducing potential, we said that that potential V is equivalent to the work done per unit charge. We said that potential is going to be work done per unit charge. And remember that this being our work done, when we were deriving this, we were considering a charge Q and another test charge which we called positive 1 coulombs from our diagram. It was Q and the other charge was positive 1 coulombs. So it means that for us to get our value, the potential difference formula, we get it by the work done per unit charge, and the unit charge we are talking about here is that test charge Q, which is positive 1. So it's going to be, we substitute for the expression for the work done, the expression that we just got earlier, which is Q times that positive 1 coulomb of charge, divide that by 4 pi epsilon naught times 1 over A minus 1 over B, which is just, this is the substitution for the work done, divide that by the test charge Q, which is positive 1, which is that. So our expression is that, which is this, divide that by 1. And so our potential will end up being Q over 4 pi epsilon naught into 1 over A minus 1 over B. So this is the expression for potential, for the potential difference between 2 points. And our value of A is the distance between Q and A. A is the smaller distance and B is the longer distance. So it means that A, which is the shorter distance, should come first, and then B, which is the longer distance, should come later. Thank you for watching. I would encourage you to subscribe if you want to watch more of these videos. Otherwise, for the benefit of your colleagues that would like to watch this tutorial, simply share the video. For Kisembo Academy, this is Arnold Ranga Kuramia.